guys, how are you? I hope you guys are very doing good. Today we are going to discuss about the part 2 video of the Verilog HDL series, which is introduction to Verilog HDL. This is also a introduction to the Verilog HDL. The first four parts of this lecture will be introduction to the Verilog HDL because I want you guys to make get into the world of digital system design. Okay, so you must know these details in the sense what is the flow, what is the flow that we are going to do. For example, if we are going to see some software codes, uh, those are like writing codes and just testing, they will see the output. So but whereas in Verilog or digital system hardware designing, so there will be some of the flows. If you understand those flows, what is the plan, what is our plan, why we are going to write all this stuff, well, actually why we need Verilog HDL, all this point if you are going to understand, okay, then it will be very easy to you guys to write the code. It will be easy for the 30 to 40%, okay, if you know all this stuff. So before learning Verilog HDL, you should need some basic knowledge related to digital electronics. So even though if you don't have, you can able to understand. But if you have a minimum basic knowledge about in the digital electronics, you will come to understand this Verilog HDL in detail. Okay, but if you want to code for the digital system designs, you should have the knowledge of digital electronics on your tongue. In the sense, uh, if anyone asks you about any FSMs or million more emissions, you should be your answer should be so quick. Okay, so we have to learn digital electronics very uh, thoroughly before entering before writing the code in Verilog HTML. To learn the Verilog HTML concepts, okay, you need basic digital electronics information is enough. It means you can start the Verilog and the digital electronics parallelly. If you start Verilog and digital electronics parallelly, you come to know, and it will be so much interesting to you guys. Uh, Learning the AI concepts in the class and learning the biological concept clearly. And if you gonna code yourself and observe the simulation synthesis of codes, it will be so good. Okay, that experience will be so good. Even I do felt that. I didn't felt that because after learning the digital electronics, I started learning digital. It will be like a recap for the digital electronics. Yeah, but I'm not gonna discuss any design part in the sense how we are going to design a AND gate or OR gate. But I'm gonna uh, discuss about the what are there in Verilog HDL, where they are gonna use by us. So this is most important in the coding part. If I'm gonna discuss you guys with the design code of some aggregate XOR gate, it will be like no fetching to you guys, right? So what I'm trying to do is I will discuss about the what are there in logical, why are they, why are they present in logical, and where we are gonna use those topics. Okay, so you guys be patient for the first four videos because it's a very theory part, and I'm making these videos to make you guys to come into the world of digital system design. So from the fourth video onwards, that is data types, I think so. Yeah. From the data types onwards, you will be very interesting. You get very interesting. That's my promise. Um, First four videos will be like very slow. In the sense, I am gonna explain very slowly because um, you even can't able to understand. I know. because but even though I have been making this video is to make you guys to make you guys have it and to make you guys to have a clear idea or a minimum idea what we are going to do while designing Verilog HDL. So let's dive into the topic. Today we are going to discuss about uh, let me introduction to Verilog. What is hardware schematic? What is hardware description language? What is meant by design functionality? What is verification? Section of Verilog code, Testbench code. Okay. Introduction to Verilog. A digital system such as flip-flop can be represented with combinational gates like NAND and NOR. Yes, because we are gonna represent flip-flop or any other circuit using NAND and NOR. NAND and NOR because NAND and NOR are the universal gates and NAND and NOR has some advantages compared to other gates. Those are low power consumptions and we can implement any other circuit using the NAND and NOR. And NAND especially has some advantages like the rise time and fall time. The rise time and fall time of NAND gate is same. The rise time and fall time of NAND gate is same. So these many advantages will be there using NAND and NOR gate. And in CMOS, while we are going to implement NAND and NOR in using CMOS, we will require less amount of gates, less amount of NMOS and PMOSs. In the sense, one PMOS, one NMOS is required to implement NAND and NOR. Yeah. Rise time and fall time of the NAND gate is sorry, rise time and fall time, yeah. Rise time and fall time of NAND gate is both are equal, both are symmetric in nature. In the sense, charging and discharging will be symmetric in nature. Yeah. The functionality of flip-flop is achieved by the connection of certain gates, yeah, certain gates in a particular manner, right? Is it correct, right? So for D flip-flop and XOR flip-flop, JK flip-flop, there are same gates in the sense, same number of gates or same type of gates, but the connections in between them will be changed. Those will be in particular manner, okay? Based on those manner only, we are going to get that functionality, right? How we are going to get that particular manner? How like this we have to connect like this if we connect like this then we are can able to achieve the D flip-flop functionality and if we cannot like this we can able to achieve the JK flip-flop functionality. How we are going to get based on the TT in the sense truth table, right? TT truth table. So the truth based on the truth table the functionality we gonna reduce the functionality using the K-maps, okay, or the Boolean formlets, okay. Because of this, the large circuit becomes very, very small. The advantages of becoming making large circuit into very, very small is area, power, and delay will be reduced. Previously, computers are the size of room size. Okay, now the computers are the size of uh, the a, uh, rectangle size, right? A plank size. Okay, or we have also mobile phones, right? We'll reduce it, and transistor size will be this. Okay, this much of size will be there in previously, but nowadays the transistors in this line, in this small line, there are millions of transistors. Yeah, that's the thing. Means the VLSI incorporating more number of uh, transistors on a single chip. Okay, in this small line itself, we can expect millions of transistors nowadays. But in previously, this square is there, right? This square in this square box. This is the size of the. uh, transistor. Now the transistor size will be our hair. Uh, Hair is there, no? It will be like if you cut the hair into the pieces, 1 million pieces, 1 million pieces. In that 1 million pieces, if you take one piece and you cut it again 1 million pieces, we will get the in that also we will get one part, right? That much of size. It means we can't able to imagine also. In the sense, it will be we can't able to imagine. We can't because it will be in nanometers or some other meters. Yeah. So let's the two table is nothing but I discussed right this. The truth table is nothing but the table tells us what inputs combine together to give what values of the output. So this is the truth table, right? What inputs are there and their combinations. If you have two inputs, we will be get four combinations, right? So based on those input values, we will get corresponding output values. So we have an example of D flip-flop in the next slide. So this is the D flip-flop where this part is the S using the NAND gates only, where this part is the SR flip-flop. So if you're going to take this as this input will be S and this input will be R. If you are going to apply one input D input to the S and the D bar input to the R, here we are going to use the NAND gate. We are going to give same input to the validate. Then we will get the D bar. We're going to apply D to the S and D bar to the R. We will get the functionality of D flip-flop, right? So we are going to apply the clock, okay, clock. And if you're going to take the truth table, we have a reset where we are going to apply the reset in the sense. So if you're going to take this, I forgot to draw it, reset. So there will be some other navigate over here. Okay. There will be bubble. Okay. Why? Because if you're going to see this, you're going to see this truth table. This truth table is valid when clock equal to passage or clock is 1. Then only this truth table is valid. When clock is negate or 0, then the output will previous output or it is don't get or it is 0 based on the situation, okay. So when the clock is on say and at the time at the point of time when the reset is 0, then irrespective of the input d irrespective of the input d the output becomes 0, okay. The output becomes 0. It means it is acting as a active low reset. If you're going to take reset as 1, when the clock is 1, the output is following the input D. So when the input 0, D is 0, the output is 0, right? So we are going to take the active low reset over here. So I forgot to draw this, which is my mistake. So this is the thing about the flip flop. Yeah. What is hardware schematic? Hardware schematic is a diagram that shows how combinational gates should connect to a particular hardware functionality. Hardware schematic is nothing but it's a diagram. Diagram in the sense, it is like this only. It is a diagram where several number of gates will be there. There are five NAND gates, right? Five NAND gates. So how these gates are connected? Here these gates are connected like this. Based on those uh, details we were going to code, right? So all these details will be present in the form of diagram. Actually, this is the hardware schematic, okay? Based on this diagram or some other diagram, hardware system diagram, we are going to code, right? So actually contains the gates and their how they are going to connect. In this case, we have five NAND gates, and there is a particular pattern for the NAND gates connection, and we are going to get the particular hardware functionality, that is D flip-flop functionality, right? Okay, let me sorry, D flip-flop number functionality, right? Next, in this case, it is set of NAND gates, right? Connected like shown towards in the previous slide, right? So if we know that values of input contribute to make the output value 1. So we know, right? Whenever the clock is high and reset is high, because the reset we are going to use here is at the low reset, right? So it the output Q follows the input D, right? So in essence, the output Q will be D. Okay, so right. Yeah. Then we can essentially hide the internal details of the connections and the expense locked into the black box. In the sense, when you know these details, like when clock is high and reset is high, uh, the output will be QD, right? So you just know these details, and when clock is low, the output will be zero with respect of the any uh, input or reset. So it's a functionality detail, right? When you know this, you don't need it, how the connections are made in the block. Inside the connections, how the NAND gate is connected, these gates are connected, how these gates are connected, with this gate, like this. This type of details you don't need if you have the functionality, right? So that's the point. This block provides with certain inputs and output that is similar to the hardware schematic made for combinational logic circuits. Yeah, it works. Yeah. What is hardware description language? Hardware description language is nothing but I discussed it, right? You know the functionality, right? Uh, that clock is high when clock is high, and also when reset is high, we will get the output QS D, right? So this is right? This is a functionality. To to implement this functionality, uh, you must write a code, right? To write a code, we need the hardware description language. Okay, hardware description language is nothing but the description of the hardware in the form of code is nothing but the hardware description language. Okay, so it is easier when we describe how the block should be behaved. See, here in the case I discussed the DT block, right? And let the software tool convert the behavior into the actual hardware schematic. So actually, we are going to write the code using the schematic only, or using the truth table. In behavioral model, we use this truth table. In gate level model, we use schematic to write the code. After writing code, we will check the design using the TV. We are going to create some test cases and run it. And if everything is fine, we are going to convert that code into the gate level netlist or the hardware schematic. We are going to see using the writing the code using the hardware schematic, and we are getting the hardware schematic. Then why is the what is the use of this? So you may ask this question, because in this the first case we are going to write the design code using this hardware schematic. Okay. In the second case, we have generated the design hardware, generated the hardware schematic using the code. It's a big thing, right? It's a very, very big thing, right? So in a sense, we are going to, in the first case, you are watching movie, right? You are watching movie. In the second case, you yourself you yourself taken an idea from the movie and you directed a movie. So, which is the big thing? The second one is the big thing, right? Because you have taken some inputs, you have designed as it is. The second is when is a very, very big thing, right? So, that's the thing. In the first case, you just draw it in paper, but in the second case, you have generated it using a code. So you guys should appreciate yourself uh, while writing these codes. Okay. Next, a language that describes how the hardware functionality is Verilog is classified as hardware description language. So we are going to describe some hardware functionality. Okay, that's the point I'm going to stress so many times. I will stress in this video, next video, and after next video. After onwards, I don't stress. I will discuss about that types and all those stuff. Okay, why I'm going to stress is if you know this, it will be easy to you guys to write how to write code. You will be able to understand. So be patient and listen these classes, 4 classes, and afterwards you guys will tell me to continue for 2 hours or 3 hours of lectures from the fourth video because the fourth video will be like that. So what I'm trying to say is listen these classes very carefully to understand the flow. Just you guys understand it. Even if you don't understand, don't worry. While we are going to work, you will be able to understand. Okay. Yeah. So what is verification? Before coming to this, we will know in detail about the design functionality. Okay. What is meant by the design functionality? Some typical behavior requests for a developer. Let us see. Okay. So clock should be an input to the flop, right? Flop in the sense flip flop. Flop in the sense flip flop short name. Okay. Yeah. If the active low reset is 0, then flip flop should be reset. Reset in the sense output will be 0. Output Q will be 0. Set in the sense output Q will be 1. Okay. So when the active low reset, right? I have discussed it previously, right? Active low reset is 0, then the flop should be reset. In the sense output should be 0, irrespective of the input, right? So it's a one functionality of the default, which we have seen in previously. It's a one functionality, design functionality of the default, right? So if you are going to say, if the active low reset is 1, then flop output should follow the flop output Q should follow the D. It means whenever the reset is 1, the Q will equal to the D. So this is also a functionality. Okay, this is also a function, another functionality of the D flip flop. This is one functionality. This is another functionality. When this going to happen? When this all stuff is going to happen? Whenever the clock is high, then only this things are going to happen, right? Whenever the clock is l- low or we negate, then these things won't happen because the output will be 0 or don't care directly or the previous state. Okay. So if you're going to see the experiment, the out Q should be get a new value only at the passage, only at the passage, not at the negate. Okay. So this is also a functionality, design functionality. So we are going to consider all these 3 points. Okay, all these 3 points and write a design code for the D flip flop. We will write a design code for the D flip flop. Okay, so now you guys have written the D flip flop code, but you have to check it, right. So whether you are getting the same values as per the truth table or not, and we are getting the functionality, same functionality or not, you have to check it right after reading the code. Okay, so an important question comes to mind. How do we know whether the behavior described in Verilog accurately reflects the intended behavior of the design? This is the question. So it means you are going to write the based on these 3 functionalities, you are going to write the code for the D flip flop. Okay, correct. Then how you guys able to know that uh, it will work as it is like a D flip flop? It may work like a surface flop, or it may like a JK flip flop, right? We don't know. You have written. You thought that yeah, this is D flip flop code. You have written, but you can't able to say that without testing, right? Exactly, it will be work like a D flip flop, right? So to do this, you must test the design code. You must test the design code. So what we are going to write with the functionality, we are going to write the design code with the functionality. For D flip flop, there is these three functionalities, right? We have seen, right? So for other circuit, there will be some other functionalities. So we have to write that particular functionality design code. After writing design code, you must test this design code. You must test the design code. To test the design code, you have to apply the inputs and output. Inputs and observe the output values that are you getting the perfect outputs or not. It means you have to check the functionality of the truth table. Okay. So to check the functionality of the truth table, for example, if you are having the two inputs circuit, then the combinations of the two inputs will be four, right? If we are going to have the eight inputs, then combinations of the circuit will be 128, right? If you are going to have 10 inputs, then the combinations of the input will be 1024. Can you apply 1024 manually? Yeah, even you can apply 1024. Okay. Can you apply 2 power 20 in the sense 2 power 20 inputs can you able to apply or not? See me the answer. So we can't, right? So we can't able to apply those many of uh, inputs, right? So we do the randomization. Okay, randomly we check. All these concepts will be covered in Verilog and system Verilog. Okay, I will discuss there. So what the point is to apply these inputs also you have to write a code for the design, the functionality of the code you have doing the writing the design code to verify this design code, you have to write the TB test bench code. Test bench code. It means we are going to write two types of code. One is test bench code and design code. Why the test bench code? What will test bench code represent means the functionality of our digital system design. In this case, we are going to describe the functionality of the D flip-flop, right? Similarly, why the test bench is required means to test that D flip-flop by applying some inputs. Those are called as test vectors. Okay, those won't be called as inputs for your sake of understanding. I am saying those as inputs. You should spell it as test vectors or test cases or scenarios. Okay, yeah. So, what we need actually to convert into the hardware schematic, either it may be the test bench or the design code. So, our main aim is to convert this design code into the hardware, right? So, the design code is always synthesizable. Okay, always synthesizable means it must be synthesizable because it is not synthesizable means synthesize means converting the code into the schematic or the diagram. Okay, circuit diagram. Okay, you think like that. Okay, it means the design code should be converted, right? Whereas TV, we don't need to convert it, right? So TV is just for the purpose of applying the inputs. Remember this point. Okay, we will create TV using the SV and UVM. Okay, and we will write the design code using the Verilog. SV and UVM are next topics, next subjects that are related to VLSI, TV business. Okay, so those will be also discussed by my yeah. So the thing is, what I am going to stress from the past 5 minutes is we are going to write two types of code. One is design code. Let me One is design code. For the design code include the functionality of our digital system. So to test the digital system design code, we must apply some inputs. Applying inputs, large amount of inputs manually is very difficult, right? So we are going to write a code for those inputs also. Those that code will be called as test bench code or the TB code, which contains test cases or test scenarios or test vectors will be there. And TB is not synthesizable because we don't need TB to be synthesized, right? So we just need TB to apply the input vectors or the test cases to the design code, right? Actual aim is to convert this design code into the schematic, right? So our aim is to convert this design code into the schematic. While doing that process, we have to verify that design code, right? So for that verification, we have to apply inputs, right? For inputs, if we are going to apply inputs, then we should apply more number of combinations to reduce time and all these factors. We are going to create test win. That's it. Okay. Yeah. Next, see the what is verification. Okay. So what is verification? That means where is this? This is checked by the different methods and is collectively called as verification. Verification is nothing but the applying the test cases or the test vectors or the scenarios using the DB to the design code. The most common widely practiced method of verification is circuit simulation. So actually we are going to simulate circuit simulation in for some of the labs like EDC lab or some other labs, right? Similarly, in Verilog lab, we are going to simulate. Okay, but here we are not going to simulate the circuit. Here we are going to simulate the design code, right? There are software tools to understand how design hardware described in Verilog should behave and provide various input stimuli in the sense it is also it is like a stimuli. Stimuli in the sense input vector I told right. Test vector, test cases, test stimuli in the sense plural, stimulus in the sense similar. Okay. Stimuli to the design model. The output of the design is checked against expected values. Expected values in the sense truth table values. We have truth table, right? We have to compare, right? If your design code is you have uploaded the TB, you have uploaded the TB stimulus to the design code. You are getting some result. You are getting some result. So you are applying the TB to the design. So you are getting some result. How do you say that the getting output is correct? The getting output is wrong. So we must compare with some of values, right? So we are going to what is our reference or the uh, reference is truth table, right? If you get the functionality of the truth table, then we can able to say that the circuit is correct. If you didn't get the functionality of the truth table, you can able to say that the circuit is wrong. Okay, that's the thing. Here the exported value is that's the thing. Okay, yeah. Next. All simulations are performed by EDA tools like Cadence, Xilinx, Vivado, Costa Sim, models. So all these are the tools which are going to be used in Verilog design. The Verilog HDL is replaced inside an entity called Testbench C. This point is nothing but I will discuss while discussing the code. In the sense, you have to instantiate the design code into the Testbench to apply those input. Okay, to apply those stimulus or input vectors or test vectors or test cases. Various tests provide different stimulus. Different stimulus is different test cases or the different input values to the design, such as TV shown in the image. Okay, this is the TV image. This is the actual the our circuit. Okay, the flip-flop, right? So when we are going to apply the TV, we are going to clock generator will be there. It is generate. We will generate using the. We will write this code also in TV. Our actual design is this only. So we get the output. This as we don't get the circuit. Remember, I'm just saying we will get the circuit while synthesizing. So this is the circuit we got it. after synthesizing. Okay, so actually we first simulate and synthesis and again simulate. Okay, this is the process. Okay, so we got it. This is a circuit. We are going to apply inputs. This input, how we are going to apply using the TV. Okay, this reset, how we are going to apply using the TV test bench. In test bench, we give this. Okay, this clock also we are going to give using TV only like this. Okay, 10101110 this stuff. Okay, so based on those inputs given by the TV, we must instantiate this module in TV. In the sense, uh, this module should present in TV to apply this inputs. Okay, we have to call this module. Okay, then only we can able to apply these inputs, right? So based on this input test cases, the corresponding output will be get, and we will compare this output with the actual values. The that may be TT, which is truth table, or some other functionality. Okay, if everything fine, then we will generate the gate level netlist and further process will be taken. Next. So this is already completed, right? Yeah, sections of Verilog code. Sections of Verilog code is from this on we will slightly introduce it to the design code and TV also. Okay, yeah. Sections of Verilog code. All behavior code could be described within keyboards, module and module. So the basic element of the Verilog code is started with module and ended with the end module. Okay. We start the code with the module and end the code with the end module. Okay, rest of the design code will mostly follow the given template. Okay, let's see the template. So module is keyword and module is also keyword. There is no space between and module. Okay, remember the point. And module is the smallest unit, or uh, you can say anything. Okay, it's the smallest unit or the one, or we can able to say like this. It is one system or the one design. Okay, next Verilog section template, module definition and port declaration. Port declaration in the sense we have some inputs outputs, right? When we are going to take a D flip flop, the D will be input, right? And clock will be input, right? And reset will be input, right? Reset will be input, right? And the output will be Q, right? So we have to declare this. So we have to declare in the sense the D, comma, clock, comma, reset are inputs. We have to save it to the while writing code. We have to say uh, mention this information, and we have to mention that Q is as output. Okay, and the input and output are also keywords. So I will be discussing the code. Okay, yeah, list of input and output ports. Port list in the sense we will give these names only. After giving these names, we will list which of these are inputs, which of these are outputs from this list. Okay, port list means we just give the names. These are the ports that we are going to have in my design, like that. Okay, after we are mentioning those ports, we are going to give the inputs, which of them we are going to use as inputs and which of them we are going to use as outputs. We will tell in the design code. Okay, next declarations of other signals using allowed without data types. Sometimes we have to require some internal signals. Okay, which are not even output and input. If you're going to take uh, if you're going to do the 4-bit repeat carry adder, the internal carries will be neither input nor output. So they are internal. They are been internal, right? So we have to declare those signals using the data types only. We shouldn't declare this as inputs and outputs. At the end, the inputs will be inputs and outputs will be which are going to appear to us only. The internal signals which are internally traveling from one module to other module, those can't be able to treat as a inputs and outputs. Okay, what are we are going to able to see to the outside world at the end product, those will be considered as input and outputs only. The internal signals like this, okay, like this, we can't able to declare it those as a input and outputs. Okay, to declare them, we use some data types like wire bridge. Okay, design may depend on other Verilog modules and hence their instances are created by module instances. We can instance, it means we can't call Verilog modules to implement other module. For example, for ripple carry adder, we have four full adders, right? For we can create a ripple carry adder by calling four full adders to the ripple carry adder module. Firstly, we can write the process is firstly we can write the replicate full adder code and TV. We can test the full error code and TB. For one full error and TB, we can test the code. After testing this, everything is fine. We have to create the one module named as replica adder. In that module, we instantiate this particular full adder four times. Instantiation means we are calling this particular full adder because replica adder has four full adders, right? 4-bit replica adder. So we will call this full adder four times, okay? And use this module uh, without beginning again from the scratch. We will call these modules. Okay, this particular calling is called as instantiation or the instances. Instances means one particular full address is called as instance, and half adder will be called as instance, and it means one particular circuit will be called as instance. Okay, so we can call these modules to other modules, which is called as module instantiation. Calling that particular module from one module to other module is called as module instantiation. Calling in a sense, it will be replaced by its hardware equivalent. Okay, it will be replaced by its hardware equivalent. Yeah. First, the actual Verilog design is for this model that describes its behavior. Okay, so firstly we're gonna use the model keyword and we are going to give that the module name, particular name. For example, I'm gonna give make the full adder. I give the full adder. Okay, it is called as identifier. There are some rules for the identifier. Similar to C only will be there, but there will be some changes. Those will be discussed on the fourth video. So that stay tuned to this channel. Okay, full adder. We can give this name as full adder if you want to make it. I'm taking an example, or we can give it as D flip flop as previous case we have taken, right? If BF. Okay. We're going to give the port list over here. Port list in the sense, what are the inputs, what are the outputs not. So combinedly inputs and outputs will be given there. We are not declaring over here. We can able to declare over here only which of them are inputs and which of them are outputs. We can declare over here, but uh, we are going to give either we are going to declare here itself or we can declare outside also which of them are input, which of them are output. But here we should give what are the inputs, what are the ports are there. Either it may be input or input or output. Okay, yeah. After giving what are the actual ports are there in the particular digital system, we are going to declare input ports among this port list. Among this port list, what are the input ports we have to declare, and then what are the output ports we have to declare, and then declaration of other signals. I told right, intermediate signals in case of RCA, ripple carry adder. Okay, yeah, intermediate carry signals, right? So those type of signals will be declared here. Only which are going to appear to us to the outside environment should be. declared as input and output based on their functionalities. Okay, the internal signals which are going to transfer from one module to other module, we shouldn't declare them as uh, the input and output both, because if you are going to take those as inputs and output, we should create a pin while designing. Okay, so we shouldn't do that. Okay, because we don't require, right? The output we don't require. With the internal, in the case of repertory adder, we don't require the internal carry signals, right? We require actual output at the end. What is the sum of the two 4 bits? Yeah, we require actually that, right? So the thing is that, okay, what are we are going to what the input ports and output ports that we can able to see from the outside, we should declare them as input and output. Other signals which are going to use in the intermediate, those should be declared using the data types wide at range. Yeah. Other module instantiations if required. So I told, right, for RCA we instances 4 times data, right? Those instantiation can be done here. And behavioral code. If any have behavioral code, we can write over here, or any some other data code for any other thing. Gate level, we can write these codes. Okay. Yeah. Next, we have to end module, because we have started this module and we have to end this module. There is no space between the end and module. See this. Okay. Yeah. Example. If I'm going to take the example, here the module is declared DFF. DFF is the D flip-flop. This is the module name. Okay. So here, previously I told, right, we can neglect this. Okay. You can neglect this and just give the ports. Here we don't give any uh, input and output declarations. So we are given ports. Actually, we are going to have 4 ports. One, two, three, four. Either you can able to give like this, and you can declare afterwards like this: input. Afterwards, input D comma D comma reset like this. Okay, you can declare also like this, or you can here itself you can give input followed by output, or output followed by input, anything. Okay, so you should separate it by commas. Okay, input to the design should be start with input. The input is a keyword. Okay, yeah, output of the design should be start with output. Okay, so we are going to declare output as reg data type. Reg in the sense, the output must be stored while we are going to use in always block and behavioral model. Those will be discussed by me later. Okay. So defaultly, if you are going to didn't mention any data type, this is the port. This is not the data type. Input and output are not the data type. We are to just declaring which what is the input, what is the output. That's it. So defaultly, the input and output ports are in the form of void, in the form of void data type. Remember this point. It will be also discussed by me later. Okay, and here the output is wire, right? So it is declared as reg. Okay, we can also give this reg as inside the block also, output reg. Okay, output reg also you can able to give like this over here only, over here only you can able to give. Sometimes in some simulators it doesn't take over here, then you must give over here. Okay, declare a variable to store our output to values. Always at the rate passage clock begin. Always at the rate is a behavioral block which will be executed uh, infinite times, and the changes will be occurred according to the passage clock or the events displayed over here. At the rate means the event. We are going to specify events in the sense. The always block will be changed based on the event list provided over here in the braces. Okay, begin is like a curly braces in C. We should start with begin. If we have only single statement, we shouldn't use the begin. Okay, if you are going to start begin, you must end the block after your okay. See, if reset and if reset if exclamatory in this is not receptant. In the sense, previously you've seen it, right? Whenever receptant is equal to reset is zero, in the sense receptant is equal to reset is zero. Whenever reset is zero, the output is zero, irrespective of the output is zero, right? The output Q is zero, irrespective of the D input. We are not considering any D input, right? That is the thing we are specifying. So here, when reset is zero, then reset bar will be one, right? So when you are not mentioning equal to one, it will default to take it as one. Okay, this is the point. It will be similar to the C only. Okay, it means the actual meaning of this is reset bar is equal to one. Okay, we haven't specified any begin after if, right? Because we have only one statement. Then Q will be zero, right? Previously in the starting slide we have seen, right? So next, else. We have to mention any begin and end in this block because there is only single statement. And else. After in else, the else in the sense the reset will be one, right? When the reset will be one, the output Q will be followed the D, right? So at the passage of the at the passage. Why? Because we have mentioned in the event list we have mentioned the changes should be taken for every passage of clock, right? So if reset is one, then you should get the D. We have to end because we have started the begin, right? So we must end. Okay, and also we have started the module, right? We must end module. Okay, that's the thing. This is an example of the D flip flop. Now let's see the okay. The portion role previously described the behavior of D-type flip-flop. The first few lines replace a new module called D flip-flop, define the input and output ports. Okay. The only other signals used in the design is Q and is declared next. Since this is a simple code, it is not depend on any other modules. Yeah. See, here we didn't instantiated any other module. Okay. For default, we didn't instantiated any other module. We just described the behavior using the behavior model and we written our code, right? Yeah, we didn't instantiated any navigates and all this stuff. Okay. Yeah. And the always block describes how the hardware should behave during certain events. So I told, right, at the rate means event. Certain events means whenever going to mention the passage clock, for every passage of clock only that always block will be work in the sense will change the output if there is any change in the inputs specified in the always block. Okay, so for every passage of code only. That particular code is belong to behavioral code. Okay, yeah. Next, this is the DB. So we must declare again. We must give the keyword TB. So we have this is the TB name. Okay, you can able to leave. You shouldn't mention any port list over here and TB in the sense you can able to give like this also braces and yeah. Declare input and output variables to driven to the design. So in TB, always the input should be rich. I will discuss all these points. Okay, just remember. Okay, you will get to know. Okay, and output will be white. Okay, in the sense the TV clock we have taken clock, right. This is TV for the D flip flop. Now previously we have written design code. Now we are going to write the TV code, which is the for the D flip flop, which is we are going to write, generate some test cases. Okay, yeah. The TB clock. Okay, this is TB clock is uh, input in the D flip flop design code, right? So we must take it as reg. So because inputs are reg, should be reg. Same D is also input, right? So we have taken it as reg, and reception is also a reg, right? So we have taken as reg. Where Q is a reg, right? Q is a reg, and also output over there in the flip flop design code. So we have to take it as while. Okay, next. Create an instance of the design. So we must create the instance module instantiation. I have told, right. We have to use this some models. We have used the full adder in repeat carry adder like that I told, right. So we have to must instant the design of the code which I have written in TV. Okay. So we are going to instant. This is called design instantiation. Okay. So what is the model of the design code that we have written? DFF, right? So we first should write the DFF, okay? Because it's the module name which we have designed. So next, DFF0. What is this then? It is the name of the D flip flop. It is optional. So it will be generated like this. D. So remember, I am just saying uh, the TV never generate. Okay, I'm just saying it is the instance name. We're going to give like this. Okay, what is the first DFF meaning is the module name which you have given for the design code is DFF. So we must give it as DFF. And where DFF not is the instance name. Okay, so we are going to give the uh, details of the thing. Connect clock input with TV clock. Clock input means that clock. I have given clock in D flip flop, right? Design code, right? So we must do specify. This is the which I have this is the clock in the design code of the D flip flop. Okay, this is the clock for the TV. So we are connecting both. So to connect both, we should give dot and which is in the block which is in design and braces inside we have to give the clock which is in the TV, okay, related to that. Next, similar to the D input and similarly to the reset and similarly to the dot Q, which is means similar to the output. We have to connect, okay. Instantiation means we have calling the T flip flop, right? And we have given some instance name and we are connecting those design code signals and TV signals, then only we can able to get the output and we can able to know, right. Then only when you are going to write the next slide we will write some code. That code will be reflected that values that cases will be reflected into the design code and those will be tested and again will be get back to the it. In a sense, simply if we are going to know means instantiation means here the design block which itself will be generated like this. Okay, while you're doing the if you're going to generate the schematic after synthesis, you will get a TV block. Okay, TV block in a sense, if you get drawn the TV block, there will be some inputs. There will clock generator some inputs. Okay, those are going to apply to the D flip flop. I will show you in the last. Okay, so essentially the hardware will be generated. Okay, we have to declare uh, we have to connect the signals in the TV and the signals in design code. Okay, then only the design will be tested. Okay, next. We have connected everything. We know we have to generate the stimulus. Okay, stimulus images, test cases. We are going to see here we drive the TV with certain values. Okay, since the TV signals are connected to the design inputs, the design will be driven within the TV. Okay, so that's the thing. Okay, the design will be driven within the values in TV. Okay, we have connected right the design inputs and the TB inputs and design output and TB output, right? So based on the design TB inputs, TB test cases, it will be applied to the design inputs which are there in the design, and based on those functionality, based on those inputs, we will get some output, right? So that will like that we will get output and we have to compare later. Okay. Next, initial figure. Initial is also a uh, it's also a behavioral block which will only execute once. It will not execute like infinite times, like always block based on the event. Okay. Yeah. Beginning is used to country basis, which is used when there are more statements. Okay. We are going to give reset as 0. Reset as 0. Why you are going to when the reset is 0? It is one test case. Okay, we are going to give reset as 0. In the sense, then only the circuit will work right based on our design home. Okay, we are going to give clock as 0. Clock as 0. Okay, next we are going to give D as 0. Okay, and and module. In the sense, the clock is 0, right? Yes, it is negate. Negate or some initially the clock is 0. We can't able to say it may be a negate, okay, or positive. We can't able to say because uh, 0 means this level, right? 0 means this level, right? 1 means this level. But here the value is 0. It's not the negate. Either it may be transition from the negative positive to negative, negative to positive. Okay, the input is 0. So here the value is 0 and this is 0. Okay, this is 0. All these three are called as test cases. Test case. This is one part, one test case. Uh, okay, we have given only one test for the sake of example. So I given an overview. What is what like that? Okay. I within the one class we can't able to discuss all these topics. I hope I have given you an overview. And the TV is the Verilog container module that allows us to drive design with different inputs and monitor its output. Monitor its output for expected behavior. Okay, we actually instantiation the design code in the TV and we are going to apply some inputs within the initial block and we have to monitor. There will be some keywords like dollar monitor, dollar display, all this stuff. Those will be discussed in the concepts. Okay. Now just I am giving an overview. Okay. We have instantiated the flop design. Flop instantiation means calling the particular design. Okay. We have instantiated the flop design. Illustrated and connected with testament signals. Okay, the testament signals then assign certain values and eventually driven as inputs to the design. Right? Why the testament inputs are driven to the design? How they are designing? How they are driving the design because we have instantiated and we have connected the instantiation nothing but connecting the we have to call that block and we have to connect the inputs and outputs in the TV and the design code. Then only we can able to test the design, right? When we are going to connect those, then only the input signals from the TV will be applied to the design inputs in the design code, then those based on those functionality which is written in design code will be tested and again that particular output will be returned to the TV. Okay, I am saying that return right. So it's actually not going there and doing this task and coming back. It's not like that. When we are going to instant check the design code, that circuit itself will be generated. Okay, we don't need to go somewhere and again execute and come to this place like we do in software code. The design itself will be generated. Okay, so this is the thing. Thank you guys. Like, share, and subscribe to LOGICS. The first four videos will be pretty boring. From the fourth video, you guys will comment. I don't ask you guys to comment. Um, you will comment definitely. I'm much very confident. So, what I would like to tell you guys is what is each and every student needs an instant tea, instant coffee, like that instant content. Okay, if you learn the instantly, if you are very brainy, it was okay fine. So what I'm trying to tell is, if you invest more time, then we are going to learn more things. Okay, so I don't wanna discuss all this stuff. Simply, I can start with the data types and all this stuff. But why I'm gonna discuss all this stuff is to give you an overview. It's like a trailer. Yeah, it will be like this, like that. So, all you guys need to invest time. You have to invest time. Okay, and we have to have a clarity what we are going to do, why we are going to do, how we are going to do. This clarity should be there. Without clarity, you're just watching some YouTube videos or only me my some other videos. So all I can promise you is whether my English I'm trying because I'm trying a lot to speak without any hesitation and all this stuff. But and also I'm taking so many retakes also for the videos. So what I'm trying to tell is I can promise you one thing. I don't know am I able to deliver the 100% content or not, but I will make you guys feel clarity about each and every concept related to Verilog in the future coming videos from the fourth video of the Verilog series. The first four videos will able to understand by you when you watch these first four videos again after completing the whole Verilog HDL, you will come to know, okay, this is the thing that we have uh, done, like that you will feel right. So I'm gonna tell you trailer. It will be like suspense. Oh, what is this? Sometimes you feel like, what is this? It's like a shit. You feel like that. Okay, it's quite natural. Even I do. I do feel like that. While learning, what the sir is telling, what he is telling like that. But after I experienced it, yeah, it's a good practice. Sir told me in front only, but I can't able to catch it like that. I felt it. So you guys also will feel like that only after when we are going to enter into the whole of Verilog. Okay, from the fourth video. Again, two videos are there. One is basic flow design and the other is some basics. And okay, I will discuss all those in the pre next class. Thank you guys. Good night.